Well, we might as well go ahead and just work through this. So for those of you watching the video later, I encourage you to work on this problem first and then go ahead and see how we find the solution here. But let's go ahead and do this. It's not too terrible. The funny thing about this particular problem, if you look at it, is you might actually already recognize, you might not, but you might recognize the left-hand side already is a product rule. Like it doesn't actually, you don't actually have to do anything to make this work. We're going to, but like this left-hand side, this is the derivative of y times e to the negative 2x plus 1. Because the derivative of y is y prime, and the derivative of e to the negative 2x plus 1 is negative 2 e to the negative 2x. So we're gonna, it's kind of gonna be funny. We're gonna do the first order linear usual process the short way, but we're gonna see that like we could have kind of skipped it if we wanted to. So let's go ahead and rewrite it in the standard form. There's paper here. So I need to isolate y prime. So I'm going to divide everything by e to the negative 2x plus 1. So let's see here. So I'm going to get y prime. I'm actually going to write it as plus, right? Because I like to write it as plus y times the p of x function. So it's going to be negative 2 e to the negative 2x divided by e to the negative 2x plus 1. And sadly, the right-hand side does not simplify in any nice way. It's just e to the negative 2x minus 1 over e to the negative 2x plus 1.
Oh, wait, no.
No. Right, yeah. Right, it'd be lovely, but it doesn't do anything nice. Okay, but that's, so we did part one, right? That's the standard form. You got y prime, and it's either good to recognize or to label things here, right? You got y prime plus y times your p of x equal to your q of x. So now we're going to find the integrating factor. So we're just going to find mu of x equal to e to the integral of p of x. If your integral of p of x is somewhat complicated, I recommend not writing e to the, like just doing the integral on the side and then coming back and be like e to the whatever. So let's go ahead and find the integral of p of x, which is going to be the integral of negative 2 e to the negative 2x over e to the negative 2x plus 1 dx. And this is certainly set up to be easy to do. This is supposed to be an easy use substitution, because hopefully we can all recognize that the derivative of this bottom part is exactly the top part. So if we let u equal e to the negative 2x plus 1, then the derivative is going to be e to the negative 2x plus 0, or I should say e to the negative 2x times negative 2 plus 0, and then times dx. And that's exactly the top part we have right here. So this is going to end up equaling the integral of just du over u, which is the natural log of the absolute value of u plus c. But really, we don't really worry about the plus c or the absolute value. We're going to say it's the natural log of just e to the negative 2x plus 1. I will point out here, just because it's worth mentioning, technically here you can actually get away with dropping the absolute value because e to the negative 2x plus 1 is always positive anyway. So you really don't need the absolute value here, which is great. So back to our integrating factor here, that's going to equal e to the natural log of e to the negative 2x plus 1, which is just going to be e to the negative 2x plus 1. Okay, great. Time to find the solution. Oh, look, this is going to work out pretty great because we're going to have to end up integrating mu of x times q of x, but we're exactly going to get the denominator canceling here. So it's going to work out pretty well. So our solution is going to be y of x equal to 1 over mu of x, which is e to the negative 2x plus 1, times the integral of q of x e to the negative 2x minus 1 over e to the negative 2x plus 1 times mu of x, which is e to the negative 2x plus 1. And then these e to the negative 2x plus 1s definitely do cancel, which is great. Makes life easy. Otherwise, it's probably pretty hard. So then we're going to end up getting 1 over e to the negative 2x plus 1. And we're going to be integrating e to the negative 2x minus 1. Yes. At this point, I would probably just write this as 1 over e to the negative 2x plus 1 times the antiderivative is going to be e to the negative 2x divided by negative 2 minus x plus c. And so I should actually write out my solution as y of x equal to that. I kind of ran out of room here. So our solution is y of x equal to, I would probably, no, I don't care. I don't care. 1 over e. I'm just going to write the same thing again, which feels kind of dumb, but oh well. I might write this as negative 1/2 e to the negative 2x minus x plus c, more just to justify that I rewrote it again than any other reason. And without any initial conditions, that's it, we're done. Cool. I don't think you have any questions about that, Reed, so I will move on. Yeah. All right, so that's pretty much all she wrote as far as differential equations in this class. That I should point out, I imagine most of you aren't taking other math classes after this, but there are certainly lots and lots and lots of other types of differential equations. Whole fields of mathematics are dedicated to studying differential equations. But as far as this class is concerned, we're just talking about separable or first order linear differential equations. That's kind of it. I suppose someone could ask on an exam, is this a separable differential equation or a first order linear differential equation, or is it neither, right? You might, that could be, I think that would be a good question personally. I don't know what your teacher's thinking, but if I wanted to test students' comprehension of the idea, I might go in that direction. Okay, so now let's completely shift gears. I feel like this class kind of goes a lot of different directions. So we've done differential equations as much as we're going to do it. Now we're going to talk about 3D graphing. And I will say the main thrust of why we talk about 3D graphing here is because we want to eventually talk about optimizing functions of two variables. So we're going to talk about functions of two variables, which lends to a third dimension, because just like when you talk about functions of one variable, you're in two dimensions, like y equals f of x. If you have some y equals f of x is going to be a function in two dimensions, essentially, right? Something like this. And then later on, after we talk about how to build up the machinery, we're going to talk about something like z being a function of x and y. And the idea kind of is that this is going to be a surface, which is still a function, but now in 3 dimensions. And my kind of, so I will definitely point out, drawing skills are important here. My drawing skills are not excellent. They've certainly gotten better over 20 some years, but they're still not great. So take it with a grain of salt. Certainly it's good to practice, but when I think about a 3D surface, I'm thinking about something like we have our X, Y, Z coordinate system, and maybe you have something that's doing kind of like, I try not something kind of wavy, like maybe it looks kind of like this. That's pretty good. So there's like your surface, your function of X and Y, where the height of the surface depends on what the X and Y inputs both are. Before we're going to get to any of that, we kind of need to make sure we understand how to graph things in the 3-dimensional coordinate system. And the first kind of thing is to talk about how things are set up. So let's plot the point 2, 4, 3 in 3 dimensions. The standard way of orienting the XYZ coordinate system is the way I've drawn it here, where X is kind of pointing out at you, right? If you could actually draw in 3 dimensions, you're imagining the X-axis pointing towards you on the paper, the Y-axis pointing to the right, and the Z-axis pointing upwards. So that's always the situation. And sometimes it can certainly, I want to say here, the amount you kind of rotate your x-axis by can make it easier or harder to draw your particular picture. So sometimes you have it kind of way out that way. Sometimes you have it pointing way more towards you. Either way is fine, just to think about how things are going to look. And then here's what I'm going to do. I know I want to go 2 in the x direction, right? Because this is an x, y, z point, just like, right, we typically write our ordered pairs or ordered 3 tuples in alphabetical order. So I'm going to be going, mark things off here. Something else to think about when you do this. The marks or the little units on the x, on the y and the z axes should be the same length, right? One length here and one length here should be the same. But the idea here is you've taken this x-axis and you've tilted it towards you so that, right, basically it's going to look like this distance here, right, that looks like that. When you tilt it this way, it's going to look shorter. So the x-axis, the distances should look a little shorter than the y and the z, if you're trying to get that perspective right. It doesn't have to be perfect, but we kind of try to do a good job here. So let's see. Let me grab some other colors too. We'll have a ruler too. Okay. So if I try and plot this point 2, 4, 3, I'm going 2 in the x direction, 3 in the y, or sorry, 4 in the y direction, and I'm using all my colors here, and 3 in the z direction. Okay, so then what I often do is I kind of just draw a box, and you're not doing a lot of plotting of just a single point in 3 space, but it's good to think about how you would do it. So for this box, I'm going 4 in the y direction and 3 in the z direction. So I'm thinking about going, well, I've gone 4 in the y direction, and I've gone 3 in the z direction. So this point here is the point 0, 4, 3. And then I can do kind of the same thing in each of the 3 planes. So I can go 2 in the x, right? I'm going to do this first. I'm going to go 4 in the y direction, and then from there 2 in the x direction. And going in the x direction is always the hardest part because you basically have to travel parallel to the x-axis that you've drawn. So I'm going to do like that. This is where you might actually use a ruler, right? Like I might take this ruler and then kind of slide it over here to make sure. See, I didn't really get that quite right. Make sure I'm going kind of parallel. And then same idea here. For the y-axis, I'm going to go from that point where x equals 2, I'm going to go 4 in the y direction. I'm going to go like this. Again, you don't have to do it perfectly. I'm just trying to make it look nice because, you know, people are watching. So that's going to be the point. X is 2, y is 4, and z is 0. And then I'm also going to, from this point here, I'm going to go 3 up. Kind of, the colors almost appear. It's fine. So I'm going to go, yeah, expose. No, that's fine. That's fine. I can use whatever colors I want. So I'm going to go 3 up. Now, I don't actually know how much 3 up is, but I'm going to go also this way 2 over. And that point there would be the point x is 2, y is 0, and z is 3. And then finally, from this point here, I'm going to go 4 to the right. And from this point here, I'm going to go 3 up. And from this point here, I'm going to go 2 over. And that point there, that's going to be the point 2, 4, 3. So typically, when I'm trying to draw just a single point in 3 space, which is what we typically call this, I draw a box where the corner I want is kind of the corner that's opposite the origin. That makes sense? It's kind of a pain, but it's the way that lets me draw it where I feel like I've actually put it in the right spot and I can kind of see, oh yeah, I came out 2, I went over 4, I went up 3. You can certainly do less of this, like you could maybe just go 2, 4, 3 and not draw all these other lines as well, but do what makes you feel comfortable. So a couple things to say about this, and we could do more, but it's kind of the same, right? It's kind of the same thing over and over again. It gets actually, let's do one more just because it can be kind of a pain if you're going into the negative parts. So let's say we want to plot the point. Do I want to plot it on the same axis? Not really. Let's say we want to plot the point. Let's go 3, -2, -1. Let's try and be slightly more efficient. So here I shouldn't just draw the positive parts of X, Y, and Z. I should draw the full thing. So I'm going to do this. Sometimes people use the convention of labeling X, Y, and Z on the positive parts of the axes. That's the positive x-axis, positive y, positive z. And then we're going to give ourselves some little marks here. Okay, let's see how this goes. So first I'm going 3 in the x direction. I'm going -2 in the y direction. So instead of going 2 to the right, I'm going 2 to the left. And I'm going -1 in the z direction. So instead of 1 up, I'm going 1 down. Okay, and so this is where things are going to get a little bit challenging, because you can see here, if I go over here and here to see where that point meets, it's almost on top of the point that I've already drawn. Now, I mean, not actually, because it's down and over, but you know, you can't draw all the things perfectly. So here, if I try and get these here, that point right there, it looks like where I've gone left 2 and down 1. Kind of annoying, not gonna lie. And then I want to go 3 in this direction. So if I go first 3 in this direction, again, here's where I would definitely, I like to use the ruler for the X parts especially. It just helps me. Do like that. Let me go in like that. Yeah, that looks maybe okay. I don't know. And then we're going to go 2 to the left here. See, things are getting messy. So there's the point where I've gone left 2 and 3 towards you is the way I'm saying it. And then finally from here, we can go down 1. I go down 1. Which would be the same as if I went 3 to the left this way, 3 towards you this way. I might have picked a bad point. That's fine, it happens. And so we could complete this picture. I don't think we really need to necessarily. Right, I don't feel like I want to draw the whole entire box, although you certainly could. I should have labeled these points as well. Sorry, that's -2 there. It's -1 here. So far you've seen I've gone 2 left, 3 towards you, or 1 down and 3 left. And then there's also this point here, which is 2 left and 1 down. Right. So I didn't kind of do, I guess I could do the whole thing. Fine. I could go, I've gone 1 down and, oh my gosh, brain. Sorry. Oh yeah. So this is, oh yeah, see, this is where it's super confusing, right? Because it looks like from here, like it looks like this is going all the way through here, but it's not. It's going from here to there. And then this point's going from here to there. That's annoying. I find that annoying. Okay, so I've got the back. Ooh, let's do this. I've got the back face of my little rectangle over here. I've got the side face of my little rectangle over here. And I don't quite have it, but if I from 3, if I go down 1 and then left 2, we can see the front face of the little rectangular box over here. And if you really want, you can go down 1 and out 3. like that to get this right side face of my rectangle over here. I feel like that makes it maybe a little more clear, maybe not, I don't know. Anyway, here's your point. 3 towards you, 2 to the left, 1 down. Okay. Let's say a few things about graphing in 3 dimensions. So first of all, some analogies. In 2 dimensions, there are 4 quadrants. And we typically number them 1 through 4, starting in the upper right quadrant. So quadrant 1, quadrant 2, quadrant 3, quadrant 4. X, Y. That's the typical labeling of your quadrants. In 3 dimensions, we have a similar idea, kind of. So in 3 dimensions, there are 8 octants. Just like a quadrant is 1/4 of the whole thing, an octant is 1/8 of the whole 3-dimensional space. And so typically, when we talk about these octants, only one of them gets a name. So if you go positive X, positive Y, positive Z, this upper right-hand corner, that's the first octant. So the first octant is where everything is positive. X is positive, Y is positive, Z is positive. And so you might do the following kind of thing. So if I think about, if I just look at the first octant here, I'm going to kind of draw part of the XY plane. Or is what I think of as the floor. So there's your XY plane. Notably in the XY plane, which of the 3 variables is equal to 0 in the XY plane? Right. In the XY plane, Z is equal to 0 because you haven't gone up or down. It's very, very analogous to how in the 2-dimensional coordinate system on the y-axis, or I should say, if you're on the x-axis, y is equal to 0. Same kind of idea. Whatever thing you happen to be on, the other variable is 0. In the same sort of way, if we look at the XZ plane here, or the left wall, as I like to think about it, this XZ plane is where Y is equal to 0. Because you haven't moved left or right. And thirdly, this back wall here, this is your YZ plane. And on this plane, X is equal to 0. That's a pretty useful thing to be aware of. We use it often when we're trying to graph things. So the first octant is the octant that's like, above this blue plane, to the right of this red plane, and forward of this green plane, where all X, Y, and Z are positive. And there is no numbering for the other octants. No one ever is talking about the second or the third or the fourth or the 8th octant. The only one I could make a convincing argument for, I feel like, is to label the 8th octant as the one where everything is negative. But other than that, there's no like the second one's the one where X and Y are positive and Z is negative, right? There's no like way of doing that. We talk about the first octant, and that's kind of it. Let's see what else I want to say about this. When I'm thinking about this in like, if I'm trying to visualize things in a room, I might, if I was sitting in a classroom facing the forward, I would look at the left front corner of the room, which I'll try and show you guys. Maybe. That's not great. It's not super helpful. You can kind of see the corner down there, kind of. I'm thinking of the bottom line there as that's where the board is. That's my y-axis. This upward edge, that's my z-axis, and this other left edge as my x-axis. And I'm imagining myself sitting in the first octant. So if you imagine facing forward again, the left lower corner of the room as the origin, then we are all sitting in the first octant of space. kind of, it's helpful. I use it to imagine things. So that would also mean that the board is your YZ plane. The floor is your XY plane, and the left wall is the XZ plane. Okay, cool. So let's talk about some graphing skills here. Yeah. Yeah. So let's graph something like black here. So let's graph y equal to 4. And it's good to think about how things work in 2 dimensions versus how they work in 3 dimensions. So I will just point out in 2 dimensions, y equals 4 looks like this. It's a horizontal line. Oh, there's one other thing I was going to say, but I'll say it. So I go up 1, 2, 3, 4. And there's my y equals 4. Now, the important thing to observe about this is that if y equals 4, what has to be true about x? Or really, like, what can you say about x? Kind of nothing, but more specifically, x can be anything. So if you've got y equal to 4, or more specifically, if you're missing some other variable in your equation, that often means that other variable can range over all possible values for that variable. So y equals 4, you get the horizontal line where y is always 4, and x takes on any real number value. So if you're graphing in 3 dimensions, y equals 4. Yeah. So in 3 dimensions, you're still going to get y always being 4. But now x and z can have any values. So instead of getting a horizontal line that extends forever and ever, and x being whatever you want, you're going to get a vertical plane now, because we're going, well, let's actually draw it. So we go over 1, 2, 3, 4 to y equals 4. Then what we're saying is, okay, well, y is 4, but x and z can be anything. So I can extend upward if I want, right? In this direction, totally fine. I can also extend downward. I can also extend in the towards you direction, right? In the x direction. And let's try and be, yeah, I think the ruler, I'm a fan of the ruler. Not that you have to use a ruler, but you might find it helpful to do so. Even then, my line is not quite parallel. Oh, well, such is life. So we can see that we can actually extend in any direction. So what we end up getting is we get a plane that is parallel to the XZ plane, but is shifted 4 over to the right. So we're getting something that's kind of like this. And this is where you're only going to draw some of it, right? Because you can't draw the entire plane, just like we can't draw the entire line. Right, but here is my plane. Y equal to 4. Y equal to 4, and x and z can be anything. So maybe you're going to get the point. Here's one point on my plane. 0, 4, 0. And here's another point on my plane. I don't know, let's say I moved, 5 in the x direction and 6 in the z direction. 5, 4, 6. All right, it doesn't actually matter what the x and the z are, it just matters that y is still 4. So I moved, 5 this way and 4 this way and 6 that way. Get 5, 4, 6. And same, so basically, whenever you have one variable equal to something, you're getting a plane. Because the other 2 variables can, and specifically, you're getting planes that are parallel to the, I don't think there's a good name for like the standard planes, the XZ plane, the XY plane, or the YZ plane. So for example, if we wanted to graph, I can put this on here. Yeah. Let's do this here. I like to try and label things somewhat. If I want to graph instead something like z equal to 6. Well, same idea. Oh, and here's also the thing I was going to say before. You don't have to absolutely draw your XYZ coordinate plane this way, although you should, because that's the way your teacher's going. I assume that's the way your teacher's going to do it in class, right? He drew it this way, I imagine, or did he not? Okay, it's most likely the way your teacher's going to draw it. But what I will say, generally, sometimes people do like to orient things in a different way because they find it helpful to visualize something. But however you're drawing your coordinate system, you should always follow what's called the right hand rule, which is where if you put your fingers in the X direction and curl them towards the Y direction, your thumb points in the Z direction. And I should say specifically, if you point your fingers in the positive X direction and you curl them towards the positive Y direction, your thumb should point in the positive Z direction. That's what's called the right hand rule. Again, when you use your right hand, that's why it's called the right hand rule. Don't do it with your left hand because it won't work. So if I want to graph z equals 6, well, I'm still going to do the same sort of thing. I'm going to plot, I'm going to draw my X, Y, Z coordinate system. And now I'm going to have Z equal to 6. I'm just going to go up to 6. And from there, I'm going to extend in the other two directions that I haven't already used. So I'm not just extending up or down because Z is what's set, but I'm going to extend right and forward. I wish I was better at drawing parallel lines, to be perfectly honest. And then do the same over here. Try and make it look good, but it doesn't have to be perfect. He says we'll try and make it look perfect. I'm a fan of kind of scribbling in the plane to make it look like it's there. Obviously not necessary, but I like it. I think it looks good. Cool. So there's our plane. And then if you were to draw both of these planes on the same coordinate system, you would get their intersection. Sure. So, for example, if we draw both y equals 4 and z equals 6, I'll try and be a little bit more quick about this. So, yeah, here's where my skills are start to waver. That's okay. So z equals 6, 1, 2, 3, 4, 5, 6. And even though this could extend way to the left and way to the back, it's usually easy to draw kind of in your wheelhouse. So I'm just going to extend this to the right and to the forward because that's just easier for me to draw. Try and draw this line parallel here. I will say parallel lines are kind of important here because if you want your plane to look not wonky, the sides kind of need to be parallel to each other. So there's my plane z equals 6. And then if we go 4 to the right here, 1, 2, 3, 4. So we do that upwards. Come on, James, you can do this. Should have measured. No, you shouldn't measure. It's too much work. You're not trying to do all the work in the world here. So these planes, they intersect in that line. Right here. So points that lie on both planes, or in other words, lie in the intersection of both planes. If they intersect, lie on the line. And we often just call a line capital L. And no, I wouldn't say that. I'm trying to say, like, do I want to say things? No, not really. What's kind of annoying about this line is without more advanced methods, there's not really a good way of describing this line, unless you're going to get into vectors and stuff, which I don't think we really do. So there's a line, it's the intersection of those two things. I should mention, not all planes will intersect each other. Planes can certainly be parallel to each other and never touch each other. We've already drawn some, right? Like the plane y = 4 and y = 0. Those are totally parallel to each other and never going to touch each other. All right. So what if I wanted to, let's draw, I'm going to leave off the name for a second, but we're going to draw x squared plus y squared = 9 in 3 dimensions. But first we'll do it in 2 dimensions. So you're going to see a lot of these probably in this section, or at least a fair number of things like this. It's good to remember that x squared plus y squared equal to some number squared, or even, equal to some number, which might look like the square of something, but will always actually be the square of something, right? Even if that was 5, you would still have a circle where the radius, which is, I should say, in 2 dimensions, this is a circle with a center that's at the origin and a radius that is the square root of 9, which is 3. So in 2 dimensions, no big deal. You get the circle, radius 3, great. So you might think about this for a second. In 3 dimensions, we're going to do the same sort of thing, except this equation doesn't have one of the 3 variables in it. It's missing z, which means we can extend it in the z direction. So if I try drawing this, let's see, yeah, sure, fine. So I'm going to draw my circle of radius 3 in the xy plane, which is always a little bit challenging, right? It's hard to draw circles flat because you're going to have to change your perspective. So we'll try and draw this flat. I'm going to label some points. So let's go 1, 2, 3, 1, 2, 3. I don't really want to label in the x direction. I kind of just want to kind of draw it. See if I can make it look right. That looks pretty right. There's my circle in the xy plane. Then I might go label this point here as well, or draw it so it looks like it's 3 out. And then the idea is that z can be anything. So we can totally just lift this circle up or push it down, so that if we go up as much as we want, and so here's if z = 2, and here's if z = 3. And so on and so forth. We can just keep going up and up and up, or down, 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 down. The idea being that we can extend this as much as we want in either the up or down direction. So in 2 dimensions, this is a circle. In 3 dimensions, this is a cylinder. Okay, now you might view this and be like, yeah, James, totally looks like a cylinder, right? Just a circle that's got length, and it is. And now I'm going to say something that might sound kind of dumb, but it's the way we talk about math, so I'm going to say it anyway. So let's graph in 3 dimensions, z = x squared plus 1. And often when I'm going to graph something in 3 dimensions, I like to at least think about what it would look like in 2 dimensions first. So in 2 dimensions, if I was graphing z versus x, again, I'm going to think of x being like the horizontal axis and z being the vertical axis in this example, because it makes sense, right? You want the function thing to be your vertical axis. That's just going to look like your usual parabola shifted up by 1. Okay. So now if I'm graphing this in 3 dimensions, I'm just going to extend it in the direction of the variable that isn't there. So to go 3D, we're just going to extend this in the y direction. Now, graphing this is going to be a little challenging because if we're doing this in the usual XYZ orientation, that means the parabola is going to be kind of vertically towards you because you're in the XZ plane, right? We're in the XZ plane here. And then we're going to extend it right and left. This is where I'm not going to say I'm going to fall apart, just that I have to be very thoughtful about my graphing. Yeah, sure. So I'm going to try and draw this in the, so I'm going to be up one. And sorry, let's label these things here, X, Y, Z. And then I'm going to be parabola, but like, yeah. So what I want to think about is like, I'm going to draw something kind of weird. I'm thinking about how this line here that's going through the Z-axis, all those are at the same height, right? If I'm thinking about this being in the X direction, this point here and this point here are both the same height above the X-axis. So I'm kind of thinking about my parabola maybe doing something like hitting those 2 points there like that. That looks okay. Not great, but just fine. And now I'm just going to kind of try to draw that again to the right. So I'm going to shift this over. So I'm not to the right. Now this might be a good time to use a ruler and measure something just so you can get the values to be the same length. Maybe not. I don't know. I feel like I get a little anal about my pictures because I want them to look really good and I'm trying to draw them for students. You all can probably be a little bit less. He tries to pretend like he doesn't want to draw perfectly. And then we're just going to draw that same parabola over here. I should have moved this point over the same line as well. I was thinking about it carefully. Sure. Okay. So then we're going to do that. We'll try to draw this parabola over here. Cool. So there's our shape. And here's kind of the front side of it. It's pretty all right. I will point out, actually, so most of these notes that I grabbed from Grant's page, but I actually grabbed them from his 17B page, because that's where he has some of the good 3D graphs. He doesn't really have any of them on the 16C page. So if you're looking for nicely drawn pictures, I would go check out these. In fact, I'll probably just post this on Canvas for you guys. What I want to point out here is this thing. You know what this is called? This is called a cylinder. More specifically, it's called a parabolic cylinder. But here's the deal. If you take any graph in 2 dimensions and extend it perpendicularly in some 3rd dimension, actually doesn't even have to be perpendicular. You can extend it in a slanty way. It's called a cylinder. It's just a convention. It's actually, so this one is specifically called a right cylinder because we have extended it at a right angle from the plane that is the first picture has been drawn in. So when you're missing a variable like X or Y or Z, you're always going to get something that's a right cylinder, even if it looks super funky. So just for example, just to kind of bring the point home here, if you had some strange shape in the XY plane, maybe I'll try to draw, right, maybe something that looks like this, like a puddle, and then you extended it in the Z direction. And then try to draw the same shape up here, which never goes well for me. Sure, we'll pretend that's the same. Yeah, fine. Yeah, totally the same, right? Yes, okay. This is a cylinder. Because all we've done is taken some region in 2 dimensions and extended it in some 3rd dimension. And actually, I should say region is not the right word. Some curve in 2 dimensions and extended in the 3rd dimension, right? It doesn't have to actually enclose the region, right? This definitely doesn't enclose the region. That's still a cylinder. Cylinders are weird. Or at least the way we've named things, cylinders is weird. What else do we got? What time is it? Oh, we got a few minutes. Okay. excuse me, let's graph a couple more things. So let's say I want to graph. What have I got here? Z equal to Y. Okay, so first of all, when I see this, I notice the X is missing. So I know I'm going to be taking some shape and extending it in the X direction. Z equal to Y is a straight line. Ooh, yeah. So here's something to point out. Before I draw Z equal to Y, well, in fact, actually, it might make sense to draw Z equal to Y first and then put in the X coordinate next. Here's Y. Z equal to Y should just look like your good old 45-degree angle kind of thing. So like here's, yeah, do I really want to? I have to think about this. I don't want it like that. Feels kind of wrong to me. I feel like it should be more. I really should look more like this. Right, there's my Z equal to Y. So here's the thing I want to avoid. I want to avoid drawing the X-axis in the exact same direction as that, because then otherwise trying to extend it in the X direction is going to look really, really weird. So I'm going to draw my X-axis kind of very like this, pointing out at me. So then when I extend this in the X direction, it looks like I'm actually doing something. So if I extend this in the X direction, like down to here, and then also, the same deal. Right, it looks like I've actually got the thing I'm trying to draw. Maybe. And again, that's all right, I guess, I suppose. I should mention this is not a cylinder. Because specifically because the thing we extended in a third direction is a line. And when you take a line and you extend it, it's kind of like pulling down a shade, you're making a plane. So this is a plane. We will, with some practice, start to notice that planes basically just happen whenever you have an equation that's linear in each variable. Meaning as long as you have only x to the first, y to the first, and z to the first, and no other powers, or they're not even there, right? We don't have an x here, still a plane. So as long as you have that kind of thing, definitely a plane. So just a couple of examples of planes, examples of equations of planes. X equals 5. 2x plus y equals 6. X plus y minus z equals 2. As long as each variable either is not present or is raised only to the first power, you're definitely going to get a plane. And for this one, right, you would draw x equals 5 and then extend it in both directions. For this one, you would draw the line y equals 6 minus 2x and extend it in the z direction. I guess we could draw these. Yeah, sure. We got time. We got 1 minute. No. So I'll just say the word. So, right, we're going to extend in the y and z direction. Here to draw this one, we would draw the line. I mean, assuming we can do it, y equals negative 2x plus 6, and then extend in the z direction. And for ones where you have all three, what you typically do, unless it's the origin, like, so if it goes to the origin, it kind of sucks. But if it doesn't go to the origin, you find the x, y, and z intercepts. And then draw the triangle that connects them. And I will draw that last one real quick because it is easy. So we wanted to draw x plus y minus z equal to 2. So I'll point out that you're going to have, well, if y and z are 0, x is going to be 2. And if x and z are 0, then y is going to be 2. And if x and y are 0, z is going to be negative 2. So there's a slice of the plane that's describing. Now, the plane really is like the whole thing that happens to have that triangle in it. but we typically just draw the triangle part because it's easy. All right, that is all I've got today. On Friday, we'll talk more about 3D graphics. For sure. It's not too bad, but it definitely takes practice, so I would encourage you to practice drawing this stuff, even if there's not a lot of web work homework problems where they actually ask you to draw things. It's in your interest to try and draw some of them.